My name is Michael Griebel. I'm from the Institute for Numerical Simulation, and I will give you a short overview on what we do in the Institute with respect to parallel computing first. And then we need to know that parallel computing has two phases. The one is research by itself to develop the new tools. On the other side, it is application, and this is typically done in a compute center. So we are focusing on the parallelization research, which is our main thing. So the Institute for Numerical Simulation is part of the mathematics at the University Bonn, and mathematics is quite successful. Presently, we are 10 professors, 40 researchers, and many students. And our mission statement, I put that up here because I think it's important. The INS is devoted to the design and implementation of computational tools for scientific applications with emphasis on high-performance computing. So we are after algorithms, fast algorithms. And we have, Ms. Mutzel said that already, quite a history at parallel computing at the INS. In 1999, this is like 24 years ago, we built the Parnas 2 system, and it reached 51 gigaflops, which is nothing compared to the Marvin today, but at that time it was sufficient to get ranked at 362 on the top 500 list. So the University of Bonn has indeed a very strong tradition on the top 500 list, and I'm happy that Marvin is taking the tradition and put it forward into the future. In 2005, again, oh, by the way, this was Pentium 2, 128 Pentium 2 processors, which you well know from your laptops at that time. And we put that together with a MyRenet and fiddled around with the Fast Connect. Same thing here in Himalaya. We reached 1.6 teraflops and ranked 428 on the top 500 list, which was also quite good. It was all homemade computers, so to speak. The parts were, of course, industrial. And so we went on. Of course, this was funded by the DFG in the research collaboration, and they gave the money. And we more or less did run out a little bit of money to keep up with the top 500 list. But still, in 2010, we reached 1.5 teraflops peak. Gobi was the next one with 66 teraflops. And presently, we, in the same room, by the way, where the Marvin is, we run our Yuma cluster. We build it up right now, and it reaches 230 teraflops. So this is not a production thing, but it's a research computer. And this is what we do at the Institute. We do research in parallel computing. And why is that important? Well, usually advances in the natural sciences traditionally was done by theory and experiment. You all know that the Gedanken experiment or the lab where you do your measurements. And from that you get your science. Numerical simulation, however, is a third way to do science, to gain scientific insight, to be precise. It's especially suited when there are no measurements possible, and this happens quite often because the situation is too dangerous to make measurements. It takes too long, it's too difficult to measure, or it's just too expensive. Then the computer can serve as a virtual lab, and you can run computer experiments, maybe apply AI-based data analysis on the simulation results, validate your new models, and therefore obtain further insight. Insight in areas where you cannot get that insight in reality because the measurements are not there. I'm from mathematics, and reality for us has to be, first of all, mapped to models. These are mathematical models. This is the first step. The second one is we have to discretize these models, make it finite, so to speak. And the third one is put it on the computer and run the reality, so to speak, on the computer in a virtual fashion. And these models are classical, you know them all, three-dimensional space plus time, the classical models in physics and in all sciences. But there are higher dimensional ones like n-particle physics and chemistry, 3n-dimensional space. We have seen examples in the previous talk. N was huge. And in stochastic models, we have even infinite dimensional stochastic spaces, and this is interesting in biology, economy, and the social sciences in the end. So we span the whole science. And when we cannot do experiments in practice or they are too expensive, the idea is to put them into the computer and run the models somehow. Curse of dimensionality kicks in, and this is my personal hobby, but I don't go into that right now. So the mathematical model of reality needs to be approximated. There's a discretization needed. You don't need to know what a discretization is, but consider a standard grid. You sample your reality on a uniform grid of points. This is a discretization. And if you want to do that, for example, if you want to resolve a cubic meter down to a millimeter, and you want to resolve on top a second down to a millisecond, how many grid points do you need in space and time? The answer is here. It's 1,000 to the 3 plus 1. 3 from space, 1 from time. So it's huge. You need a lot of grid points, and therefore a lot of storage, terabytes and more. And to compute things on top of that, you need exaflops of computing time, and this means in practice on a standard computer, if you can do it at all, you need months of runtime. Of course, if you want to resolve to a micrometer or a nanometer, things explode, and this is the curse of dimension. You need huge storage, and it's very expensive. So what can you do? You can go to a parallel computer and divide the points by p processors. If your computer has millions of processors, divide it by p, and you can treat much bigger problems. The computation also gets faster. The runtime is roughly divided by p plus some data exchange and communication. And this is simple, at least in writing, but the practical reality is very difficult to make that run. This means in the end that for larger number of processors, you get better resolved problems or models. You get faster computations, and you get more accurate results in substantially less time. And this is crucial for science in the future. Finer resolution gives you better answers, less errors. Okay, so this is what we do at the Institute for Numerical Simulation, efficient parallelization of these techniques. This is an important research topic by itself, coming up with new algorithms. So, for example, this is a survey on what the people are doing. Mr. Burstedt runs parallel adaptive grid refinement and load balancing, and I want to explicitly mention the P-Forest software of him, which runs on many supercomputers worldwide. It comes from Bonn and is run in the United States, and you will see later on an example. Adaptive HP version of finite elements from Mr. Gedeke. Mr. Schweitzer does multi-level methods. I'm doing high-dimensional things. Mr. Garke runs machine learning techniques. Uncertainty quantification is a big issue done by Mr. Dölz. Ms. Neitzel is doing optimization. Homogenization is done by Ms. Verführt. Mr. Rumpf is doing imaging and variational methods. And Mr. Ganter, who will start next month, is doing isogeometric analysis. So this is our team at the INS doing the research in sequence, but also in parallel. Many of these people work in parallel. So this was the research, and I do not want to bore you further on with research. Nasty details are always bad at a presentation like this. The application, on the other side, is more interesting. What can you do with the algorithms? And the answer is you can use these algorithms on many different scales, from very tiny atomistic scale up to the macroscopic scale. And this is what I show you next in just simple examples. The first example, I'm happy that Ms. Kirchner have shown you already a carbon nanotube. This is the carbon nanotube. And you put them into a polyethylene matrix. And this carbon nanotube, it's strong as diamond. It's more or less a specific tube-like version of diamond, so to speak. And the idea is to reinforce the polyethylene matrix. You mix things and get a stronger material. Will that work or not? Well, if you throw a nail into jelly, why should that be a better material? It does not work so easily. But if you do functionalization, then, and this is a movie on that, then the force from the outside is transferred to the nanotube and the other way around. You need a connection between the two things. And then you really get better material, 30% stronger material by these techniques. So simulation can help you make predictions for new materials here. Another one is concrete. It's not so much known, but concrete or cement is a very important material. And it's not completely understood why it is so strong. The Romans used it in Trier already. And the mixture of concrete is very deliberate and very difficult. And simulation might help in this respect. Silicate chains form polymerization, long chains, and building blocks, and this give you concrete structures. These building blocks give strength. But let's go now further on in the length scale. Let's go to our length scale, so to speak. And the first application is fluid flow on that length scale. A tiny droplet, this is what you see here, deposits on a surface. This is a rubber surface. To get the data for rubber is not so easy, but if you have that, you can do computations, and it looks like this. It's a two-phase simulation, water and air on a surface. And the trick is there's a contact angle. And depending on the situation, namely on the rubber, you get different contact angles. You can measure that in the lab as well, up to a certain precision, but you can do it in the computer and save the money of the lab. This is not correct, I'm just kidding. It is a good addition and add-on for the lab people to guide their experiments. You can reduce the number of experiments to some extent. Otherwise, you have to do a lot of experiments, and what limits you is time and money. Simulation can help in this respect. A larger scale, well, you don't say much on that. Two-phase flow, a lighthouse, waves are coming in, and the lighthouse should not fall down. How do you have to build the lighthouse strongly enough? Well, the people do that since 300 years. These buildings are very strong, but you can maybe come up with better constructions, and the lighthouse still stands. And to this end, you need simulation. And you save in the material of the building. Same thing here. This is a collaboration, was a collaboration with the Bundesanstalt für Wasserbau in Karlsruhe. This is a wire in a river, and they want to get the water down. If water falls down, it has energy, and the water crashes on the on the bottom of the river. If the river is not very strong, the bottom is not very strong, then it erodes there, and you get holes in the bottom. You don't want that, and to this end, the engineers built stilling bassins. This is what you see here. This is a stilling bassin. It takes the flow, the fast flow, and makes it still, at least a little bit, and takes the energy out. Question is, how do you build the wire? And how do you build the stilling bassin? And now you can make experiments. You build the first one, it costs a little bit. You build the second one, it costs still a little bit, and then you run out of money. You cannot do much of an experiment with that. Okay? But in the lab, in the virtual lab of the computer, you can change the geometry here. You can change the geometry here, and you can optimize in this respect. And this is where a virtual lab helps you. Also engineers. And the Institute for the Bundesanstalt für Wasserbau is the biggest one. It takes care of all the rivers and sluices and wires in Germany. And they use our codes. Third one is a pile of sand. Wind is coming from this side. What happens? What do you observe in the desert, so to speak? And if you do that, well, the sand particles, millions of particles, are treated in parallel, and they get transported. They deposit in the lee side to the bottom. On the side, there are strange vortex formations, and therefore you get a certain specific structure after some time. And the geologists and these people, they study the dune formation in the desert. And what you get out of that is Barkhan kind of dune, as we will see in a minute. If you change the parameters of your simulation, you get different structures, and you can, again, play the game of the experiment in the computer. You don't have to go to Saudi Arabia and do the measurements. I'm kidding, you have to do both. You have to go there, make the measurements. But in the end, you get this kind of structure, and this is a Barkhan kind of dune. Okay, let's go on. In 2011, there was an earthquake in Japan. And Carsten Burstedt and his colleagues in Texas used the code I was talking about previously, and they simulated the earthquake over the whole world by adaptive refined grids. I don't show them. But the Earth is like a bell, and if you hit a bell, there is a sound wave going around, and this happens here as well. Here is Japan. The data are taken from the measurements of the people in Japan after the earthquake, and these are the waves after the earthquake running around the Earth. And this is a huge calculation with, on a very big supercomputer with our code, Carsten Burstedt's code, in Texas. It's a global seismic wave propagation of the Tohoku earthquake in 2011. The last thing is the largest scale. Our astronomers, they like that. Well, they observe the universe, they observe the galaxies. The measurements are a little bit difficult, and to validate a model like a dark matter model, a lambda model to be precise for the expert, we run calculations. We have millions of particles, trillions of particles at the beginning, more or less uniformly distributed. There's the model acting on that, and well, you let it evolve, and in the end, you get the one large-scale structure of the universe. Supergalaxies form in a specific pattern, and hopefully you can back interpret on the parameters of your model whether this really describes the whole evolvement of the universe. Nobody knows, but the astrophysicists are the experts, and you should ask them and not me on that. We are just doing the calculations, okay? So this was what I wanted to show you from all scales of application. And now let's come to Marvin. This is a large-scale HPC system, and such a system is essential for our university, for our traditionally modern university like Bonn. It's necessary for simulation research in all the excellence clusters, in TRAS, in CRCs, and in projects in many institutes. This virtual lab is important there. And Marvin is urgently needed for these simulation tasks, and it's an important milestone for still larger HPC system in the future to come. We heard about Marvin 2 in 5-6 years, okay? And the INS is also looking forward to use Marvin for its large production runs, complementary to its code development, which is done on a smaller local computer, namely our UMA, which is in the same building, actually in the same room right now. And some of you might know this building in Bonn. It usually looks a little bit different because it's not standing alone like this one does. This is the main railway station. And this is a not realistic simulation. So you can play around with the codes as well. So thank you for your attention.